Hello, welcome to my channel. My name is Adrian, and today we are going to continue with our GPS data that we got from Strava, and we're going to determine the energy required to run or to complete the run. Let's get started. Now, if you haven't watched my previous video, I highly recommend you go watch it, as that was where I've shown how to go and calculate total time jogged, the total distance and the pace using GPS data from your smartwatch. We then went and compared it with the data that Strava gives, and we found that we can get quite close by just using simple equations like the SUVAT equations to help us calculate the distance, time and pace using the GPS data. Now the next thing to do is to go and calculate the energy required to complete this run, and we're going to use Newton's second law, which states that the sum of all forces equals mass times acceleration. Now we've already calculated acceleration in the previous video together with the velocities, and we've put it in this variable a, so we've got that. And now the only thing left for us to calculate is the sum of all the external forces. Now I've gone and rewritten the equation as the total force that you need to overcome to complete the run is your forces required for accelerating, as well as the forces that you need to overcome due to elevation differences and the forces due to air resistance. Now we're going to start off with gravitational forces first, and we've already calculated the elevation for each time step, and this was given to us by the GPS data. Now because the elevation is ever changing, we need to go and calculate the angle between the elevation surface and the horizontal, and we're going to calculate and give that the name theta. And to do that, we take the inverse of tan and we divide the elevation with our time step. That is just normal trigonometry triangle, a right angle triangle that you can do to get theta's angle. After we've got the angle, then we can go and use sin theta to get the component of the force due to gravity that is parallel to the surface of the road or whichever you are running on, and we multiply that by the mass of the jogger times the gravimetric acceleration constant to get the forces due to gravity, either pulling you along or trying to stop you from running uphill. So we can first go and have a look at the data, and we can see it's a nice big array for each time step. But here at the start there's some irregular data, which you can see it starts off being positive 53, and then here at element number 8 it gets to where all the others are. So we're going to overwrite this first 8 points just to make our data a bit cleaner, as I've done here. If we go and we plot it and have a look, you can see this run has definitely have a little bit of hills, a little bit descends, another hill, so it's all over the place. We can now go and calculate our angle theta as well as our force due to gravity. And I've given myself a weight of 80 kilograms and the gravimetric acceleration constant is 9.81. We then go and loop through each time step and we calculate our elevation, and we can go and plot that to have a look and see that for theta, our angle between our elevated road and our horizontal, you can see that for inclines, a positive theta in radians correspond to inclines in the route, and for declines, theta is negative radians. So that looks approximately correct if we compare the value of theta with our elevation profile. We can also go and have a look and see how it looks, the forces looks like to overcome when you're jogging. And you can see again, for inclines you've got positive forces, for declines you've got negative forces, because gravity is essentially helping you along. And then again for uphills you're on your own, gravity is your enemy, and then it becomes your friend on the downhill. So that is forces due to gravity calculated and done. Next we can move on to the air resistance. Now the equation that we're going to use is this equation here, and that is essentially half times rho, which is the density of air, times your velocity squared times your coefficient of drag and your frontal area. Now I've given myself a coefficient of drag of 0.9 as well as a frontal area of 1.8 square meters. The density of air I've taken as 1.2, and then we go and we initialize our variable and we loop through each time step and we calculate the forces due to air resistance. If we plot it, we can see, if we look at the y-axis, that the values are much smaller compared to the forces due to gravity. Now, the reason for that is, if we look at our equation, we can see that this velocity squared is basically the driving factor for this forces. And if the velocity is really small, the force due to air resistance will be small as well. Now imagine if you're sitting in a car and you're driving at 120 kilometers on the motorway, then your forces due to air resistance will become much more significant and much bigger that you'll need to overcome to be able to move forward. But if you're jogging at a leisurely pace, the air resistance is not really going to be such a big effort to overcome. Obviously, if you've got a nice headwind that you need to compete with, the story becomes a bit different. So we can go and just visually show this by adding some headwind at 30 kilometers per hour, and we can see what that does to our forces due to air resistance that we need to overcome. Now, if you look at the graph, you can see that maximum is approximately 18 newtons, and if we recompute it with a headwind, that jumps up to almost 160 newton. So the air resistance, or the forces due to air resistance, becomes a lot more, and you have to start working to get ahead. But in this case, we don't have any wind, we don't have any headwind, so we don't need to worry about that. So if you start getting really fit and you start running faster, that is a bit of a negative, because the fact that you're running faster will cause the forces due to air resistance to become bigger as well. So it's sort of a, a losing battle in a sense, but exercise is good. So now that we've gone and calculated our air resistance and our forces due to elevation, we can go and calculate the total forces that we need to overcome. You can see I've put here a conditional sort of statement saying that this component, the acceleration component, is only valid for when you're accelerating, for when your acceleration is positive. The reason for that is as soon as your acceleration is negative, you are starting to slow down, you're braking, so you're not exerting any energy, or you're not burning any energy to accelerate. In fact, you're just slowing down. There's no energy required to slow down, but there's energy required to accelerate. So the total energy is only dependent for scenarios where we're accelerating for that component. So that's why I put it there. We can have a look and see what our total forces looks like, and it basically follows the same trend as the graph for the forces due to gravity. And if we go and we put all three components next to each other, you can clearly see that the forces due to air resistance is minuscule compared to the forces due to gravity and the forces due to acceleration. For jogging purposes, we do not really need to worry about the air resistance if there is no headwind, of course. Now that we've calculated the total forces, we can go and calculate the energy required in kilojoules to complete this run. So if we calculate that, we can see that approximately 187 kilojoules is required to complete this run. Now again, I've put some conditional statement here saying that the total forces needs to be bigger than 0. The reason for that is as soon as it's bigger than 0, it means that you are generating this energy to overcome the restrictive forces. When the total energy becomes negative, it means that you're receiving energy, which in a sense doesn't really make sense. And that usually happens where you're on a nice steep decline, and you could almost say that the gravity is helping you along so well that it's giving you energy, which is not possible. So for this case, I just say, all right, total energy, total forces, when it's above 0, it means you are generating that force. You need to generate that energy, so then that's valid. But for any total forces that's below 0, that does not need to form part of this calculation. If we go and we plot it, we can see again against the elevation of the track, for nice steep inclines you got a lot of energy that you require, and then for some cases where there's decline, your required energy is literally 0. And that is exactly cases where the forces due to gravity is more than enough to propel you along without you needing to generate any additional energy. But then again, when you're in an incline, gravity is not your friend anymore, and you need to do it all on your own. And that sort of shows nicely how it is to jog. Declines is a jogger's friend, inclines not so much. And that's it. Hope you've enjoyed it. If you've liked what you saw, please give it a thumbs up. If you want to see similar content like this, please consider subscribing. Thank you for watching, and I will see you in the next video. Bye.